Hello, welcome to EEE 117. Here we're talking about chapter 15, active filter circuits. This is a part 2 asynchronous section. So let us keep going. Just give you a reminder where we were last time. We talked about low pass and high pass active filters. You see two circuits here. We're using op amps with some resistors and capacitors to create that filtering effect in addition to an amplification stage. So typically it's a gain, has an amplification and a filtering stage. Okay, so we have high pass, low pass filters done. Now let's start talking about band pass filters. Okay, so remember the idea with the band pass filter, excuse me, is you have a certain range that you want to amplify and everything else you want to attenuate, right? So here, notice that we have low gain, it creeps up and then it kind of flattens out and then goes back down, right? About right here where we're transitioning from the no pass zone or the stop band to the pass band, that's your lower cutoff frequency, WC1. And then you have your upper cutoff frequency where the gain starts dropping off. And in between these two, this is your band pass region with the same bandwidth and everything else that you remember from the passive band pass version. Okay. The big difference is that the gain is going to be greater than 1. So you see you have like a gain of 20. And that's the amplifiers helping add gain to the circuit. Now to do this, we're going to take a high pass filter, which typically only lets high frequencies through. So in green, we could have a high pass filter where the lower frequency gets cut off and then at a higher frequency just lets everything through. So that would give us our lower boundary. And then we could also use a low pass filter, which typically lets the gain through at low frequencies and eventually cuts off the higher one. In red right here, we could have a low pass filter to cut off the higher frequencies. So by using a low pass filter and a high pass filter, we could kind of cut a little window in the middle to have our band pass region. Okay, and of course, in the middle of the band pass region, we won't have a gain of greater than 1. So we're going to have a third amplification stage to raise that gain up. Okay, so basically a band pass filter is literally just taking a low pass filter in conjunction with a high pass filter and then a amplification stage and smashing them all together. Okay. So the idea is we're going to have an input signal. We're going to go through the low pass filter to make sure that we knock out low frequencies outside the pass band. Whatever's left, we're going to go to the high pass filter next, and that will then knock out the high frequency signals. So now coming out of here in the middle, the low frequency is gone, the high frequency is gone. All we have left is a pass band in the middle, right here, okay? And then we go through the amplification stage to increase the signal to whatever level we want, okay? So remember, low pass filtering stage in red sets the upper cutoff frequency, right? So it cuts off high, so it'll cut off the frequency we don't need. A high pass filter will set off the lower cutoff frequency that will cut off any frequency we don't want on the lower side. Okay. Lastly, we have an amplification stage where we could multiply the gain as much as we want to make the consumer happy. Okay. So 3 main stages. And they're all in series. That's the big takeaway here. Okay. So we can see circuit-wise, where does each one look? Well, the first stage right here, this is literally a low-pass filter we talked about in the previous day, where we have an amplifier with a capacitor and resistor in parallel on the feedback side. So this is our low-pass filter. So signal comes in, goes through this RL, and then goes through the amplifier, feeds back CL, RL parallel, and this will give us our first stage. Now, we can pick RL and CL to design to cap that frequency that we want. We additionally have an RL right here. We typically match these resistors because the gain of the low pass filter, we want it to be 1. We don't want to increase the gain early on here. The last stage is for the gain. So everything before the gain amplification stage, let's just make sure the gain is equal to 1. And the easiest way to just make sure the 2 resistors are equal. Okay. In the middle in green, we're going to have a high pass filtering stage. So here we're going to use, again, the input signal come in about right here. We're going to have our resistor and capacitor in series before on the input stage. It goes through the amplifier, and then we have a feedback resistor of RH, and this will be our high pass filtering stage. We use RH and CH to calculate the cutoff frequency we need, And then we have RH and CH. We have those two, sorry, both resistors are equal because we want our gain to be 1 at this stage as well. Lastly, we have a third stage, which is the amplification stage. Notice there's no capacitor here because we're not doing any filtering. This is just a straight inverting amplifier where you have RI and RF. And you could choose these resistor pairs to create a gain that we need. We could maybe gain of 10 or 20 or 30 or 40. We could use any two resistors to get the level gain needed, right? So again, 3 stages, low pass, high pass, cutoff frequencies are set for these first two, and then we'll have our amplification design on the third stage. So let's concentrate on the low pass filter section first, the first one in red here, right? Remember we have upper cutoff frequency, that's a frequency in the higher end, because remember low pass filter, we let everything below and everything we hit at the WC omega C2 point, afterwards at high frequency, it gets shut off. Okay, so our upper cutoff frequency, omega C2, is always going to be equal to 1 over RLCL. So you can literally pick these two, and this would be your higher cutoff frequency. And then anything past that frequency, this circuit will attenuate it and cut it off. Okay. The gain we want for the low pass filter section to be equal to 1. So we just make sure both resistors are equal to each other. So our gain is -1. So we have an input signal. The gain just gets inverted to the negative version, and any filtering throws out high frequency signals. Okay, so no real amplification is done apart from the inverting part. Okay, so that's your low pass section. In the middle, the signal propagates to the high pass section, where very similarly, this is going to create the lower cutoff frequency. So remember, high pass means any lower frequency gets cut first. So think about WC1 as that barrier. Any lower frequency, the high pass filter already cuts off. Everything above it is going to let through. Okay. So cutoff frequency WC1, omega C1 is always equal to 1 over RHCH. We could choose these two to get any lower cutoff frequency we want. Just make sure the resistors on the feedback loop and the input are both RH, both equal, so that your gain is only -1. So there's no real amplification stage. So what ends up happening is a first stage, you don't amplify anything, but you invert it. So about right here, you have a negative version of it. But in the second stage, you invert it again, right? So then it's back to positive at the end of the stage right here. But you don't have any gain yet, okay, which is by design. Okay, lastly, we're going to have our third stage, which is our amplification stage. Again, there's no frequency changes, no capacitors needed. It's your standard RF over RI gain. So we could choose these two resistor pairs to have a gain of 10, 5, 12, 2, whatever we want. Okay. And note it does invert it, so you can get a negative version out here as well. Okay, so again, 3 stages going through. As long as you know how to design each individual stage, putting them all together is pretty easy, right? So we're not really doing anything crazy, in my opinion. We're just taking things where you learn and just mashing them together. Okay, so again, let's do a quick example to show you number crunching. So you have your low pass stage, your high pass stage, amplification stage, 3 of them. So let's design an active band pass filter with an overall gain of -10. So we know the amplifier will have a gain of -10. We have the lower cutoff frequency, WC1 equals 2000 radians per second. So we know the high pass filter will need to design for omega C1 to be 2000 right here. And then the low pass filter stage will design the upper cutoff frequency of omega C2 at 12,000 radians per second. Okay, so let's start with the first one, the low pass stage. We know our cutoff frequency needs to be 12,000 radians per second. So WC2, omega C2 is equal to 1 over RL times CL, right? There are 2 variables. I mean, you could just pick one. I just said, let's just stick with a resistor of 1K ohms. That's the most common one we typically see. It was an arbitrary pick. You could pick wherever you want. Just 1K just sounds like an even number for me. So you have 12,000 equals 1 over 1K times C. You just do some basic rearrangement, algebra rearrangement. The capacitor for your low pass stage, this one right here, is 0.087 microfarads, which you just go to the bin and you could pick that one up, or whatever's closest to it. Okay, so that's your low pass stage. Then let's do the high pass stage. So remember, this is your lower cutoff frequency. WC1 is equal to 1 over RH times CH, where lower cutoff frequency is 2000. Again, we have two variables. We could just arbitrarily pick one of these to solve for the other. I'm going to go the same thing I did before. I'm just going to pick 1 kilo ohms as a resistor value, just because that's a very common number. So we're going to have 2000 equals 1 over 1K times the capacitance. You number crunch this and do some basic algebra. Your capacitor is equal to 0.5 microfarad, right? So nothing too crazy. Yeah, it's just basic math. So we designed the low pass stage, we designed the high pass stage. The last one we need is the amplification stage. So I wanted my overall gain to be -10 in the pass band. So the gain is very easy. You get negative RF over RI. Again, two resistors, one equation. I could choose one of these arbitrarily. I'm going to say RI equals 10 kilo ohms because I apparently have a bunch of them because I'm using them for my entire design. And then just -10 is equal to negative RF over 1K. So RF is 10 K ohms. So we get a 10 kilo ohm resistor, put it in your circuit, and then you have a gain of 10, -10 to be exact. Okay. And again, this is by design. So this is pretty much a complete design of your bandpass filter, right? The active bandpass filter to be exact. Okay, so you saw me do it. Why don't you go ahead and do it? So we're going to have our 3 stages: low pass, high pass, and amplification. Right? I want you to design it to be, again, in -10. I want the lower cutoff frequency to be 2,000 radians per second. The upper cutoff frequency to be 12,000 radians per second. So very similar to the previous example, except I'm imposing restrictions on you. You only have 2 microfarad capacitors available, nothing else. Right, so just manufacturer kind of shortchange you and says all we have is this today. So if you want to design this, you're stuck. Okay, so we can do that. We also know we have an extra 2 kilo ohm resistor sitting by. So I'm going to say this RI right here. I want this to be 2 kilo ohms. So this is 2 kilo ohms. Both of these capacitors are 2 microfarads. You have to figure out all these resistors to make it all happen. Okay, so go ahead and figure out the low pass filtering stage here. Then go ahead and do your high pass filtering stage here, and amplification stage, and then you should have something set. Okay. So go ahead and take our 15, 20-minute break to kind of do some number crunching here. We'll come back and check your design and see how good you did. Okay. So with that being said, go ahead and pause video, and we'll come back in a little bit. So see you guys in a bit. All right, welcome back from our break for EEE 117, Chapter 15, Active Filter Circuits. We talked about active bandpass filter. So let's go ahead and design it and see how it works. So here's an exercise. So remember, our capacitors were restricted to 2 microfarads only. So remember, low pass filter stage will take care of the upper cutoff frequency here. So omega C2 is equal to 1 over RL times CO. Omega C is 12,000. Capacitor is 2 microfarads, so a resistor, just doing some algebra, is equal to 41.67 ohms. So you try to find a resistor close to that, and that will take care of the lower cutoff frequency, the upper cutoff frequency. So the low pass filter stage is done. Let's go ahead to the next one. Here we're going to do the high pass filter design. High pass will take care of the lower cutoff frequency, omega C1, which is 2,000 radians per second. So omega C1 equals 1 over RH times CH. Again, capacitors are locked to 2 microfarads. So then R 2000 equal to 1 over R times 2 microfarads. RH can be equal to 2, solving for algebra, RH is equal to 250 ohms. Okay, so just basic algebra is all it is. And the amplification stage, we want a gain to be -10. So we have negative RF over RI, right? So we said RI has to be equal to 2 kilo ohms because that's what we had extra. So then just doing some number crunching, -10 equals negative RF over 2K. RF is equal to 20 kilo ohms. Okay, so that's pretty much your design, right? Once you know the circuit and topology of it, the number crunching is very simple, which is, right? So that was for the bandpass filter. The other thing we need to look at is always the band reject filter. They're kind of both side by side. So let's talk about active band reject filter. So here is a plot for it. Looking normally you'll have your band pass in the middle. The gain will be pretty much 0 or very close, very little. Anything outside these cutoff frequencies, you should let the signal through. So at very low frequencies right here, this light blue, we should let it through. Once we hit that lower cutoff frequency, omega C1, the gain should be getting lower and lower and lower. We should try to attenuate the signal within this band range, the bandwidth. So right here in the middle, this is our stop band. So we're going to go, notice the gain is going to 0, right? Or as low as physically possible. And then at this middle point, it'll then come back up. And then we'll have our upper cutoff frequency, omega C2. After that, the gain will be high enough, we're going to let the signal through. So just like a band pass, except it's opposite. So the band reject, you get the middle part. That's where in the middle here, the signals, we're going to kill it. We don't want it. Anything outside our cutoff frequencies, we're going to let it through. So blue regions let it through. The red and green, this is the stop band region. Okay. Now, how are we going to do that? Well, what we could do is we could again look at a high pass and low pass filter. Notice that we want low frequencies through, but we want to eventually stop at omega C1. So having a signal go through at a low frequency and then killing it as it gets higher, that's a low pass filter, right? And in a high pass filtering section, we get a high frequency we want to let through, and the low frequencies we want to try cut out, right? So in this particular case, we could just look at, again, the two high pass and low pass filters together. Okay. So, and of course, after you solve the stop band region in the middle, outside the region, you still have that gain of, let's say, 20. You need to increase it. So you need to have an amplification stages as well. So just like before with low pass filter and high pass with the amplification stage, we have 3 stages we need to go through to create a band reject filter. Okay. So just the big thing to remember is the middle area we want to block and the outer edges we want to let through. Okay. So one way we could do this is we could put the low pass and high pass filter in parallel instead of series, and then after that amplify it. And after it goes through the low pass or high pass stage, we'll amplify it to whatever we want. So here, let's do some analysis. Let's say we have a low frequency signal. Now remember, the lower frequency, we won't let all that through. So any low frequency signal is going to come through this wire. It's going to hit the high frequency filter and get blocked immediately, right? Because high pass only lets the high frequency. But we can let the low frequency through a low pass filter. So in red, the signals goes through the low pass filter and goes through the summing amplifier and then comes out in output. So the low frequency passes, which is what we want. Okay, what about the high frequency signal in green? High frequency signal comes in, the low pass filter is going to block it, but it's going to let through the high pass stage. And then it'll go through the summing amplifier. Because we put them in parallel, we're letting low frequency signals through and high frequency signals through. We're letting both of them through. So it's kind of like alternate paths around the roadblock in the middle. Okay, now what happens if the frequency falls between the high pass and a low pass filter? What if it's kind of in the middle? Well, at this point, both of these filters are going to block them. So frequency, a middle band frequency to try to go through, but a low pass filter says, nope, I'm not letting you through. You're too high for me. But then a high pass filter says, nope, you're too low for me. So as long as a low pass filter and high pass filters are set far apart, everything in the middle won't have anywhere to go and it will get blocked out. Okay, so that's why we have to put them in parallel. Okay, just to go back up over here, is at the lower frequency here, we're going to let it through. The higher frequencies here, we're going to let it through. But everything in the middle, it gets blocked by both filters. Neither one is going to let it through. Okay. So that's the magic of using parallel filters. We could choose either or. Okay. So here it's kind of like conceptualizing it and towards a circuits analysis stage is our input signal goes through. We could either let it go through the low pass filter or the high pass filter and amplify it afterwards. Okay, so the low pass filter is we call it the 1A stage because it lets the low frequency through. High pass filter is called 1B phase because and the high frequencies through. And the reason why we do 1A and 1B is because technically the signal hits both of them at the same time. So it's literally a single stage. Previously, we had 3 stages, 1, 2, 3, because there's 3 separate points where the signal hits. But here, technically, the signal hits both at the same time. So we kind of just say 1A and 1B. Okay. Now, as long as the signal goes through either one of these, they eventually come to the summing amplifier. And then this thing will then be the second stage where it will take either signals and add them together and then amplify them as much as we want and then have an output, okay? So that's ideally, from a signal routing standpoint, what we're going to do. Just let either one through and then add them together at the end. Okay, so how do we do that in terms of a circuit topology? Well, at the top, notice we have our low pass filter in red. Then we have our high pass filter in green. Notice that the signal comes in and splits to both of them at the same time. That's why you have this node split off. And then after the filters, they both go through a resistor and they both get summed up to a summing amplifier. So real quick, a summing amplifier is literally taking two separate signals. As long as it goes through the same resistor here, it goes into the amplifier, it's going to act like a inverting amplifier, except we're just adding both signals together. Okay, so that's the only thing that a summing amplifier is literally an inverting amplifier, except you just have two inputs and you have to put a resistor on each input. Okay, you can't just connect these two wires together without these two resistors because these two wires might have different voltages. Okay. So in terms of the design aspect, you have your low pass stage, stage 1A, uses RL and CL. So the CL, RL up here on the feedback branch, that creates the filtering effect. And then you have RL on the input stage. You typically make these two RLs equal to each other. So your gain is 1 because you don't want to amplify on the filtering stage. Same thing for the high pass stage, stage 1B. You use RH and CH on the input of the op amp to create the filtering effect. And then you have the feedback filter resistor RH right here. As long as these two resistors are equal, your gain is going to be equal to 1, again, because you don't want to amplify the gain coming out the filtering stage. Okay, the amplification will come here on the amplification op amp. Here's stage 2, we have RF and RI. Notice these two resistors, they're going to be both the same. You don't want these two resistors to be different because then one signal will be amplified more than the other. So just make sure these two resistors are equal to each other. Okay, yeah, you see note uses two RIs for summing part. So just create you choose RI over RF to create your amplification right here as well. Okay. One thing to note, because we're going, in terms of this particular band reject filter, this is actually going to be a positive value at the end. Because note the signal comes in, either one of these stages it goes through, it will technically be a negative voltage right here in between the stages because you're going through an inverting amplifier. And then we're going to invert it a second time and get a non-inverting version right here. So it's just a little tidbit that this active band reject filter will have a non-inverting output compared to the active pass band filter, which did have an inverting output. It's not a big deal because you could just swap the polarity of the output to whatever circuit you have next. Okay, so like always, let's go through each individual stage and see the design of each stage. Again, do everything bite-sized pieces, then we'll put it all together at the end. So kind of opposite of the band pass filter, the lower cutoff frequency is responsible, the low pass filter stage is responsible for the lower cutoff frequency, omega C1. This is opposite of the band pass filter, so don't have to get those confused. So omega C1 is equal to 1 over RL times CL. So you could just figure out your capacitor or resistor based on this. And then your gain, just make sure the RLs are equal to each other. So this resistor right here in the input stage and resistor in the feedback stage, they both have to be equal because we don't want any amplification on the filtering stage right here, okay? We could do the same thing for the high pass section where we have the high pass filter down here, where we have the upper cutoff frequency, omega C2 is equal to 1 over RHCH. Again, this is opposite of the band pass filter, so just keep that in mind, right? Again, if you know capacity, you know your capacity, you can choose your resistor or vice versa. The gain, again, has to be, we don't want any amplification stage, so we just want to make sure the gain is equal to 1 passing through, so just make sure these two resistors are equal to each other. Okay. And of course, at the end, now we have our actual amplification section stage, where first off, there is no capacitors in the circuit because there's no frequency changes. All the filtering part has already been done. We're just increasing the signal. So all you have to do is just calculate your gain. It's going to be RF over RI, negative RF over RI to be technical. and we just choose the resistors to amplify however much we want. Just again, just make sure these two resistors or input stages are equal to each other. Otherwise, you're going to get some wonky. You're not going to get an equal signal coming out if they're off. Okay. So again, 3 stages put together. So kind of do an example. So let's say we have a gain in -10. The lower cutoff frequency of omega C1 equals 2,000 radians per second. Upper cutoff frequency of omega C2 equals 12,000 radians per second. But this is the band reject filter now. So topology-wise, notice you have your input voltage. This input voltage then branches off to a low-pass section and then a parallel high-pass section. And this comes out to an amplification stage. Lower cutoff frequency. So the low-pass filter, again, is a lower cutoff frequency for this particular filter. Omega C1, which is equal to 2,000. This is equal to 1 over RLCL. Again, we have freedom to choose wherever we want. I'm going to choose RL to be equal to 2 kilo ohms this time. So 1 over 2K times CL, just some algebra. Capacitor for low-pass filter is equal to 0.25 microfarad. So you could just go find one of those in the bin. Okay, so we could check off our low-pass stage. Let's do our high-pass stage right here, where remember for a band reject filter, omega C2 is equal to 1 over RH times CH for the upper cutoff frequency. This is 12,000 radians per second, which is equal to 1 over R times C. Again, I design choice, just to make it easy. I chose RH to equal to 2 kilo ohms. So 1 over 2K times C, kind of do some algebra rearrangement. The capacitor for your high pass stage is equal to 41.67 nanofarads. So it's a little bit smaller. And that's this one right here. Okay. Lastly, we got our gain stage. This is pretty straightforward. Gain, I want to be -10 right here. So I have negative RF over RI. I'm going to choose RI to be 2 kilo ohms because we've been using the same one this whole design. So we're going to have -10 equals negative RF over 2K, where RF now is equal to 20 kilo ohms. So coming up over here, this will be 20 kilo ohms, and these two will be 2 kilo ohms. Okay, and that's it. You're pretty much done with your design. Okay, as long as you know what the topology looks like, the math is pretty straightforward. And one thing people like about this active band reject filter and band pass filters, again, all we had to do is just look at cutoff frequencies. We don't really care about the band pass and the center frequency and all that. Not too much here. Okay. So to summarize everything, for active band pass filters, it's 3 stages: low pass stage in series with a high pass stage in series with an inverting amplifier. Okay. Band reject filter is the low pass filter stage and the high pass filter stage in parallel, which then gets summed into an amplifier at the end. So it's obviously different topologies here. Okay, the big thing to look at is for that band pass filter, the lower cutoff frequency, omega C1, is based on the high pass filter. Okay, the upper cutoff frequency, omega C2, is based on the low pass filter. So they're kind of opposite of what you would think. Then the gain is equal to negative RF over R. That's pretty straightforward. For the band reject filters, the low pass and high pass filters are kind of swapped in what their duties are. For here, the low pass filter is in charge of the lower cutoff frequency. Omega C1 is equal to 1 over RL times CL. A high pass filter stage is responsible for the higher end cutoff frequency, omega C2, which is equal to 1 over RH times CH. And at the end, you have a summing amplifier, which is a gain of negative RF over RI. Okay. So overall, it's just some extra pieces put together, but design-wise, it's not too complicated. As long as you just go stage by stage. Don't try to do everything at once. Just go do 1, then 2, then 3, and then put it all together. Okay. So that's all I have for this week. You now have an idea, an introductory idea of what active filters look like in circuit analysis. It's basically resistors and capacitors creating frequency changes. You're blocking signals or letting signals through. With the addition here that we're adding amplifiers to create a gain of more than 1, so we could power more bigger devices downstream. Okay. So with that being said, thanks for showing up this week and learning about this. We got one more week to cover next week for 2-port networks, and that'll be it. So hope you guys have a good weekend, and we'll catch you later. See you around.